Okay, so if we have a strong acid or strong base, this is what we are expecting the strong acid or strong base to do. So if we have a strong acid, it's going to completely dissociate. So that means every time we add an HCl molecule to water, because it's a strong acid, the hydrogen is going to come apart from the Cl. Every one of those. That's what a strong acid means. If it's a strong base, for every sodium hydroxide we add, so sodium hydroxide is a strong base, we're going to get sodium ions and hydroxide ions. They're going to completely split apart. So no more are hooked together. Okay, there's no more bond there. You get through something? Good. This is what we expect for a strong acid and a strong base. And there's some strong acids and strong bases that you have to know. So you guys have that acids bases sheet that I gave you last quarter. You saw that. Yeah, I don't have any more printed, but I can put some more. Is there anyone else who wants? So you can put it on the note on your note card, but you can't have that on the test note. Okay. Okay, I'll print off the new one. I need someone else to
Raise your hand. Raise your hand.
I'll print off 10 and then I'll have some.
I didn't get one of them. Okay, if you didn't know it. Sorry, I thought it was here. It was a big paper.
Where's the print thing? Okay, I will keep working on this, but we'll keep going. All right, so when we have there it goes. When we have a strong acid or a strong base in water, what we're looking for is 3 different species. So we added it to water, so we better have water. So species are just like, what chemicals do we have? So we have water. We also have the conjugate base, and we have the proton that we get from the acid. So there's an Alex question that's going to ask you this. If I add, it's going to give you a strong or weak acid or base. So if we're given a strong acid, we expect the proton to pop off. We expect the chlorine to pop off for this acid. And then we added it to water, so we better expect that there's some water in our solution. We can also write hydronium instead of H+. I think H+ is easier to write, but if you want to write hydronium, you can also do that. I think Alex likes hydronium, but it will also accept H+. So H+ is faster to write. Okay, questions on that. So we're looking for 3 species for a strong acid. The hydrogen ion, the conjugate base, and water. We get those 3. So I have something to look at. Okay, we're going to do it around next week in the
Yeah. It's somewhere like your range. Just wasn't he's trying to. And he got usually brands. I mean, I'm saying he didn't have to stay after school for. He got to skip school for it. And he could complete the training. So that's. And I think that.
Okay. So again, this is our list of strong acids and strong bases that you will have to memorize. If it's not on this list, it will tell you in the question. If it's it'll probably just say, "Oh, this is a weak acid." And it's on the paper. Yeah, this is on the paper, so you don't have to write that down. So again, if you don't have this paper, I will give it to you. Some of these, if it gives you a different base, I don't think it will, but if you have to name it, you know how to name the bases. You name the metal and then hydroxide. So those are a little bit easier, I think. Okay, so weak acids are going to partially dissociate. So strong acids completely dissociate. Weak acids only partially dissociate. So this is acetic acid. This is how I'm used to writing it. Usually, Alex writes it like this. Alex will accept many forms of acetic acid. So how you can pick your favorite way to write acetic acid, and Alex will accept it. But this is showing you that this proton is this is the hydrogen that the acid gets rid of. Okay. So if we have a weak acid, only some of the acid gives off a proton. Some of it stays in the original form. Some of it stays with all of its protons. Okay. So that makes it weak. It can't completely dissociate. And then weak bases is like the opposite. Weak bases only partially accept hydrogen ions. Bless you. So remember, ammonia is our base. Here, water would be our acid. So water is going to give a proton to ammonia. We get ammonium and we get hydroxide. So only some of the ammonia molecules will gain a hydrogen. So we will still have some of this original ammonia left in solution. Does that make sense? So not all of them are going to accept the proton. That's the weak base. All right, questions so far? You know, right? Does that make sense? So far we talked about weak and strong acids and bases. Yeah.
So they form solutes when they switch into conjugate acids and bases. Like I mean.
Oh, they dissolve in water. Yeah. Okay. Yes. So often, if it's an ion, it's going to be dissolved in water. Ions. For it to be an ion, it needs the water to help it charge bonds. Yep. Remember, so ionic compounds are soluble in polar, and that's because the polar molecule can help buffer those charges. All right. Oh, sometimes I can't tell if you're ready or not. Okay, so there is a same question on Alex. It will say, oh, now you have a weak acid. What species are present? Well, it's an acid, so we still have H+. We get our conjugate base, whatever the conjugate base is. But we also have the original acid that didn't lose its proton because it's a weak acid. And because we added it to water, we always will have water. So when it's a weak acid, we're looking for 4 species. We're looking for the H+, the conjugate base, whatever that is, the original acid, and water. So this section in Alex, probably like all of the other Alex sections, this is if you practice it in Alex, this will make more sense. It's going to ask you to figure out what are the species present. The best way to do that is to practice. Again, I really like to write H+, probably because I'm lazy, but H+, you don't have to write H3O+. It's the same. Alex will accept either. So you can either put H3O+ or H+. Okay. All right, we are going to switch to Alex for this topic. So we are going to try to model a strong versus a weak acid and base. So I think the trickiest one is the weak base, and I haven't done that one for other things, so I might take a minute to do that one. Let's see if I have it open actually. We might have to just draw it. There we go. Okay, so this one is called, and if you want to follow along with us on your own, that's okay. So this is called Identifying Strong or Weak Acids and Bases from a Sketch. So we have to know, so we have a weak acid and a weak base. So this is the trickier question. So give me a minute if I get it wrong. Bear with me for a minute. It's been a year. This one's a little bit tricky. Okay, so we know that when we have a weak acid, we have some of the acid is getting rid of a proton. So we're looking for something where only some of the acid is getting off a proton. So let's go ahead and look for that. So this one, we have, this is our proton, this is water, this is the conjugate base. So here, I see none of the acids have the original acid with an acid and a proton together. So this would be a strong acid because all of the hydrogens are popped off of the conjugate base. Does that make sense? So this is a strong acid, so that's not true. Okay, and then we just keep going through. So this one, all we have is hydronium and water, and that doesn't make sense because the hydronium is a positive charge. We need a negative charge to balance that, so that doesn't make sense. This one, if we look through, so we have hydronium. We have this is our conjugate base. The conjugate base gave off a hydrogen to hydronium, so that one is there. And we also have, let's see, so we need to count for that one hydronium for one conjugate base, one hydronium for one conjugate base, one hydronium for one conjugate base. So for every time we lost a hydrogen, we have a hydronium. And we have some original acid also. So I think this is the best picture so far. This is our original acid. We have 2, 3 original acids and some that have dissociated. So far, number 3 looks best to me. I can keep going through. This one has all of the acid. All of these are conjugate base, so those are all popped off. So this is the strong acid again. I think Alex doesn't like the hydrogens floating around by themselves. So this one, I don't think Alex likes this one because the hydrogens aren't attached to ammonia. Not ammonia, hydronium, excuse me. So Alex does not like free floating hydrogens. So that one's not right, even though we have some of the original acid. This is just hydronium and water, which doesn't make sense. This is an acid that didn't dissociate at all, so that's not really an acid. This is just more undissociated acid. Okay, so I think 3 for the weak acid. Does that make sense, the reasoning? Okay, this one, I can't remember. I haven't done this one for years. So the weak base I remember was tricky. And I remember that we had to think about ammonia. So let's look at ammonia. So this is a weak base. And then we add water. And we end up with ammonium, I get these confused. And we also get hydroxide. So what we're looking for, and I think this is confusing because of the way they draw it. I think they're going to draw this as a circle. And then this one is going to be a circle with the hydrogen And then we're gonna have water. And then we're also going to have some hydroxide. And I think that's how we're gonna draw this. Does that make sense? I remember this one being confusing, so if we get it wrong, we'll have to just read the explanation. So this one, we have, so notice we have, this is hydroxide, so we have this is like our base and our hydroxide, but this is a strong base because they're all completely dissociated. We don't have a mixture. We're looking for some of this and some of our protonated base. So I think that's what I remember. Okay, this is showing we have some of this base with hydroxide. Some of it's broken apart. Okay, this is where I can't remember for sure. So this, let's keep going. Let's look at all of our options. Let's see. Let's keep going. So this, we kind of have that. But we don't have any hydroxide here, so I'm not sure that one's the right one. This is just hydroxide and water, no base. This would be like sodium hydroxide, and it's not dissociated. So I don't like that one. Hi, no, you're good. Come on in. This one just has our base and water, so that's not a good answer. That's just water and hydroxide, and this is just our undissociated base. So let's go back through now that we know what's there. So I think this might be our picture. We're looking, oh no, not this one. Okay, this one might be our picture because we have some hydroxide and our bases, but this is not a base. Okay, this one we're gonna have to put on our note card. Okay, here's the weak base. Because we have ammonia, which is they're representing as the blue. And then we have some base that accepted a proton. So blue plus a proton. And then we have some water that we lost the proton from. So this is our hydroxide. So this gave a hydrogen to the base. Does that kind of make sense? Okay, so this one's confusing. This one I might put on my note card. This one tricks me almost every time I do it. So let's double check and make sure that these are right. But does that make sense, the reasoning, how we're looking at, we're looking for things that are either accepting or donating protons. Okay, all right. If you get a strong acid and a strong base, those ones are pretty easy. Okay, so those are our pictures for weak acid and weak base. Do you want to try another one of these? Okay, we'll see if we can get strong acid and strong base. So, okay, so strong acid. So what does a strong acid do?
Dissociates completely.
Dissociates completely. So we're looking for, so like, we use this to show our picture of what's going on. So we should, if it's strong, we should have none of this original acid. We should only have our conjugate base and hydrogen. Again, Alex does not like free floating hydrogens. So can you see how this has the original acid? So we can't have any of that if it's a strong acid. So that doesn't work. How about this one? This one, all of the acid is not dissociated. So that's not really an acid. This one, we have undissociated acid. This one doesn't have any acid, it's just hydronium and water. So this one, all the acid is dissociated, or all the hydrogens are dissociated. But Alex doesn't like free floating hydrogens. They have to be attached to. This one still has undissociated acid, so that's not right. This is hydronium and water. Hopefully it's this last one. Okay, so then here we have all of these blue ones don't have a hydrogen. and we have all the hydrogens are attached to a water as a hydronium. That would be a strong acid. So I think that strong acid is the easiest. Weak acid looks really similar to a strong acid, except that it has a few of the original acids with the hydrogen attached. So if we go through, then this would be our weak acid, because for every one of these, so this is like a conjugate base that gave away an H+. The H+ went to hydronium, but we also have some original acid also. So in a strong acid, we should not have any of this. For a weak acid, we should have some of this in our picture. Okay.
What about a strong base?
Strong base. So what does a strong base do? So
It breaks apart.
it breaks apart completely.
So will it look like the strong acid?
It will look like we have sodium and hydroxide. It will do like two, something like this. Should we see if we can find one?
No, well, I have one right now.
Oh, I wish I had a cable I could plug your computer.
Well, I only have
Should
one
we-
which hand.
Oh, let's try it. Let's see if I can find it. Let's see if this one will have. Strong base. Okay, so we have something like this, and it completely dissociates, like you said. So we're gonna have this. We're gonna have OH, and we're gonna have water. So this one, can you see how this is like our sodium and hydroxide? But none of it's dissociated, so that doesn't work. This one just has more sodium hydroxide, but not dissociated. This one was our weak base because it's pulling the hydrogen from the water onto the space. This one has, they're trying to confuse you about a weak base, but a weak base is not like that. Okay, that's not it, because there's no base. So here, if you look, we have like sodium ion and hydroxide. And every time we see a sodium, we should see a hydroxide. And every sodium is dissociated from the hydroxide. So this would be our strong base. We'll check that, but does that make sense? Okay. All right. And then let's strong acid again. We're looking for an acid that's completely dissociated and the hydrogens aren't free floating. So this would be our strong acid. Okay. All right. Questions on that one? Does that topic make sense? Okay. All right. So we got through that one. Let's keep going. Okay, so one of Alex's topics is going to ask you to measure the acid strength. So you're going to have to calculate this. So it's just a ratio. This is how you do that. I'm going to give you the equation, and then if we need more practice, if you need help with this one, we can talk about it next time. This is just like the equilibrium constant we talked about in chapter 7. So we use this equilibrium constant Ka, but so it's an acid dissociation constant. So remember, this is always going to be products on the top over reactants. So this is the reaction that we're using. So we have our acid. It's going to dissociate. We get hydronium, and we get our conjugate base. So when you are doing this topic, you have to count up. How many hydroniums do you have? How many conjugate bases do you have? Multiply them together, and then divide by the number of the original acids in your picture. If it's a strong acid, so remember, if it's a strong acid, we won't have any of this original acid. So if we don't have any of this original acid, then it's a strong acid. That's going to be the strongest acid. It will only give you one strong acid. You're not going to have to compare two strong acids in the picture. So I think you can figure it all out. We only have 2 topics on Tuesday, so if we need to come back and do this one, we can do that one together. So larger Ka will be a stronger acid. So you're gonna figure out the Ka for each of the pictures and then rank them based on the value. So stronger Ka will be the stronger acid. Okay, I think, we don't need to talk about that. Okay, so, how many of you have talked about the pH scale? Okay, all right. So when we get a low number on the pH scale, it is acidic. Okay. If we have a high number on the pH scale, it is basic, and right in the middle is neutral, right at 7. And this shows us some things in the lab 12, the next lab. This is part of what you're going to be doing is you're going to be testing to measure the pHs of some household chemicals. Or I think last year we did like lemons. So that's kind of a fun lab. We get to use pH paper. That's pretty fun. I know some of us are interested in medicine. I think usually biology is disgusting, but I know some of us are interested in biology. And I thought this was kind of an interesting picture to show the different parts of our body, the different pHs. So, like our stomach is quite acidic, very acidic. Most things are pretty close to neutral or acidic. This is probably the most basic. Pancreas can go to 8. So that's kind of interesting. All right, so we have to calculate the pH in Alex. So this is our equation. pH equals negative log of the concentration of hydrogen ions. How many of you have used pH in your math class? Ever? Or not pH, log. You've used log before? Okay, good. So, good. I'm glad that you have done that. So this little p means it's the negative log scale. So anytime you have a function, it's like a p in front of anything. This little p just means negative log. So pH is the negative log of the concentration of the hydrogen ions. So remember when we use these brackets, do you remember from chapter 7, what do the brackets mean? You remember? We talked about it though, you remember that? So these brackets mean we have the concentration. Does that sound familiar? So this is telling me it's the negative log of the concentration of hydrogen ions. So that tells us that this needs to be in moles per liter for this to work. So we're going to get a problem. It's going to tell us a mass of an acid, and it's going to tell us the volume. So this is our steps that we're going to use. We're going to calculate the moles of the acid. So we're going to use the molar mass. So how do we do that? If we have mass, if we have grams, and we need to get to moles, what do we have to do? Good. Yep. So we're going to take the mass and divide by the molar mass. And that will give us moles. Okay, and then the next step is, so we'll have moles of the acid, the moles of the acid. Okay, and then last time we talked about sometimes our acid has more than one hydrogen that it can give off. So look on your list, most of the acids only have one hydrogen. There's a few of them that can give you 2 hydrogens. If it's going to give you 2 or 3, Alex will tell you. But that tells you that you have to multiply by the number of hydrogens in your acid. Okay, so for example, if we had sulfuric acid, how many hydrogens could that give us per mole of acid? 2. So we would take the moles of our original acid, multiply by 2 because we want the concentration of hydrogen ions. We don't want the concentration of acid. We want the concentration of H+. So most of the time you're basically multiplying by 1. You don't have to do the step, but you need to check every time. Okay. And then you're going to calculate the molarity. So you're going to take the number of moles of H+, and you're going to divide by the volume. And then you can plug that into your pH equation. So you take negative log of the concentration. All right, so remember, Alex really cares about significant figures. So we have a new rule for pH when we're doing sig figs. So when we're using the log, So you look at how many sig figs you have in your question. If you have 3 sig figs, you get 3 decimals. The numbers in front of the decimal point don't count for 2 sig figs. If your numbers say you need 2 sig figs, then you need 2 decimal places after you do the log. Does that make sense? So we'll do one together, but that's our new rule for sig fig when we're using logs. All right, we have one more slide, so we'll do our example problem together, and then the rest of the time we can work. Okay, so this is going to be similar to an Alex question. This tells us we have 856 milligrams of perchloric acid. So we have to figure out what is perchloric acid because we need the molar mass. Let's see. So the first thing that we're going to do is find moles of perchloric acid. So right now, maybe we don't have them memorized yet. So what is perchloric acid from your list? You have it? Okay, so somebody check. I'm pretty sure that's perchloric acid. We talked about we're going to take our mass. Remember, we need to go to, this needs to be in grams first. 1, 2, 3. So we have 0.856 grams of perchloric acid. We're going to divide by the molar mass of perchloric acid. So how do we find the molar mass? Well, sometimes, I'm not sure if Alex gives us this one. Maybe Alex will give us this one. How would we find the molar mass of perchloric acid? No one remembers? Yeah. Good. Good. I'll add all the molar masses for the elements. So we have hydrogen, which is about 1. We have chlorine, which is about 34.5. We have oxygen, which is about 16, and we have 4 of those. So this is about 99.5 grams per mole. Okay, so then we divide this. 0.856 divided by 99.5. So on Alex, you're going to want to be more careful than we are being. Okay, this is number of moles of perchloric acid. So our second step is we need to check number of H+. So in this acid, how many hydrogens am I going to get out? 1. So if I have 1 mole of this, I'm going to get 1 mole of hydrogens. So we have this many moles. We have 0.086 moles of that. So I'm going to have this many moles of H+. Does that make sense? So it's not always going to be 1. This problem, we only have 1 hydrogen for 1 mole, but you need to check that every time. Okay, the third step is we need to find the concentration. So remember, our concentration is moles over volume over liters. So we have this number, moles of H+ over our liters. We don't have this is not in liters. So we need to convert to liters. So we're just gonna divide by 1,000, move the decimal place left 3. So this is our concentration of hydrogen ions. So I'm gonna take this number and divide by 0.28. Okay, and then this is molar. I'm gonna put molar H plus. We ran out of space. Okay, and then the last step is you can calculate the pH. So pH is negative log of the concentration, which is this concentration of hydrogen ions. And then how many sig figs does this problem give us? How many do we get? 3. There's 3 there, there's 3 here. We just did division, so we should keep 3. We just are gonna do the log, so that means we get 3 decimal places. Okay, so negative log of 0.3075. So this pH is 1.513. pH doesn't have units. Okay, questions? Okay. All right. We get out at 9:05 today, so we have like 20 minutes, about 20 minutes left.
Is this like the longest topic to do in the chapter?
I think the titration one that we're going to talk about on Tuesday is kind of long. But this, yeah. So I don't remember if this one is longer or that one. That's not too bad. It's maybe long going through it the first time.
But it was messed up on a single word.
So then just practice. Do lots of practice problems. Okay. All right. We have a visitor today.
Hello, I'm Patrick. I'm from Weber State University. I'm a sophomore in their chemistry teaching program. If you have any questions on like how it's going over, just let me know, and I can come over and help you.
Okay, all right. Thank you.